In this problem, it says to assume that females have pulse rates that are normally distributed with a mean of 75 beats per minute and a standard deviation of 12.5 beats per minute. So here we have our normal distribution, and we are looking at the distribution of individual values of pulse rates in this particular case. The mean, they said, was 75, and standard deviation, which measures spread, is 12.5. So I label the center, which is my mean, that's 75, and then one standard deviation above the mean would be 87.5, one standard deviation below the mean would be 62.5, and I could label out further. I don't really need to for this problem, so I'm going to leave it at that. Now, question part A says if one individual or one adult female is randomly selected, find the probability that her pulse rate is less than 81 beats per minute. So on this graph, I'm going to find 81. I'm going to say it's about here, kind of in the middle there, and draw a vertical line up. And we are looking for the probability that this individual has a pulse rate less than 81, so we're going to the left. So to calculate the probability that an individual value is less than 81, I'm going to use the normal CDF function in the calculator. And I need to give the lower boundary, upper boundary, mean, and standard deviation. The trickiest part of this is the lower boundary, and that's where we're starting. There is no lower boundary, really. This is going out to negative infinity. So in the calculator, we don't have a way of typing negative infinity, so I'm going to type -1 E99, which really means -1 times 10 to the 99 power. In order to do this, we're going to put in the negative, and that's the negative in parentheses, not the subtraction sign. Then you can put in the 1 or not. It doesn't matter whether you put it in. And then the E, you're going to press second and the comma. And above the comma, you'll see that it says EE. And so that is the E. It shows EE above the key, but then just one E when it prints on the calculator. And then the 99. So that's what I'm going to put here. And then my upper boundary or right-hand boundary is 81. Mean is 75. And the standard deviation is 12.5. And when I calculate that, it comes out to 0.6844. So that's my answer for that. Now let's take a look at part B. Here it says if 25 adult females are randomly selected, find the probability that they have pulse rates with a mean less than 81 beats per minute. So now we're going to make a distribution of sample means. The mean for the distribution of my sample means is mu sub x bar, and that's just equal to the mean from the original population. So that's going to still be 75. The standard deviation for the sample means is not going to be the same as the original standard deviation. So we can approximate this standard deviation for the sample means by taking the original standard deviation and dividing by the square root of the sample size given. So you have to have a sample size given in this situation, and then we're going to use that to modify that standard deviation. It becomes smaller with a larger sample size. So our original standard deviation was 12.5. We're dividing by the square root of 25, and you can type it into the calculator just like that, which is especially useful when the sample size is not a perfect square. But you could also calculate this and find out that we have 12.5 over 5 and divide that and get 2.5. So you can find 2.5, or you can type it in as the 12.5 divided by the square root of 25. All right, so now we are finding the probability that the mean of the pulse rates is less than 81. And let's go ahead and label our distribution here. So now we have 75 in the center for the mean, and our standard deviation is 2.5. So that's going to make this 77.5, and this would be 80, and this would be 82.5. So I'm just labeling enough that I can get a good idea of where the 81 is going to land. So my 81 should be roughly here. And then we have the area to the left is the percentage of values that would be below 81, the percentage of sample means that would be below 81, and we can see that that's quite a bit more. So let's go ahead and calculate this. And again, we're using the normal CDF function in very much the same way. So we put in -1 E99. Upper boundary is still 81. This is almost the same. The only thing that's changing here is the standard deviation. So if I were typing this on the calculator, I would quite possibly just type in 12.5 divided by, and then hit the square root button and put 25 in there. Or you could put in the 2.5, whichever you prefer. And this is going to turn out to be 0.9918, which is very believable, right? That looks like about 99%. So that's the probability that the sample mean is less than 81. So that's the difference between this problem and part A, is that we are looking for the probability that the mean is less than a certain value, as opposed to an individual pulse rate being less than 81. So now let's go on to the last bit. It says, why can the normal distribution be used in part B even though the sample size does not exceed 30? Originally, they said that pulse rates were normally distributed. So when we are using the central limit theorem, and that was where we modified that standard deviation to use the sampling distribution of the sample means. So we either have to have a sample size greater than 30, or the original population needs to be normally distributed. So since the original population has a normal distribution, the distribution of sample means is a normal distribution. So that's why that was cool, and that's the end of that problem.